Hi, my name is Colonel Amelia Duran Stanton. Today I will be presenting on medical procedure simulators in orthopedics. This briefing will discuss the current state of the technology, how these systems relate to modeling and simulation, and their current applications, strengths and weaknesses, and future directions for both civilian and military medicine. This presentation will define orthopedic simulators, examine current technologies and example systems, discuss their relationship to modeling and simulation, evaluate benefits and limitations, and conclude with future trends and military applications. Orthopedic simulators are systems designed to replicate surgical procedures and clinical decision-making in a risk-free environment. Examples include OSSO-VR, Vertamed arthroscopy simulators, and Precision OS orthopedic VR systems. Today's simulators are highly advanced and increasingly realistic. OSSO VR provides immersive rehearsal and analytics. Vertamed provides physical instruments with haptic feedback. Precision OS provides orthopedic trauma virtual reality training, and there's increasing realism and performance tracking. Several strengths are repetition without patient risk, objective performance, and standardized training. Additionally, there are some limitations: imperfect haptic realism, limited battlefield stress simulation, high cost, and limited long-term validation. Emerging technologies include machine learning for automated skill assessment, digital twin models based on patient imaging, and cloud-based collaborative simulation. These simulators are fundamentally based on modeling and simulation principles. Computational models recreate anatomy, biomechanics, and procedural interactions. They provide instrument-tissue interaction modeling and real-time performance analysis. Key modeling components include imaging-derived anatomy, physics engines, and AI-driven analytics for performance evaluation. There are several benefits. Simulation improves procedural confidence, decision-making, and communication while allowing objective assessment using measurable performance metrics. Orthopedic simulators are used for resident education, certification, trauma readiness training, and preoperative planning. Research shows simulation-trained providers often complete procedures faster, make fewer errors, and retain skills more effectively. Important challenges remain, including high costs, incomplete realism, resistance to adoption, need for additional validation studies, and technical interoperability issues. So this therefore provides difficulty proving direct translation to patient outcomes. Christensen's theory of disruptive innovation applies strongly to surgical simulation technologies. Simulation began as lower fidelity alternative, which was initially less realistic than cadaver labs. It improved through technological advances and is now transforming surgical education. Chesborough's open innovation model is visible through partnerships between universities, military medicine, and technological companies. This accelerates development and improves scalability and adoption. Raymond's open source concepts influence simulation technologies through collaborative development and shared innovation. The shared software frameworks, collaborative development, and continuous iteration, and also potential cost reduction. For future directions, future systems may include immersive operating rooms, AI-guided coaching, robotic integration, and adaptive learning. There are key trends that include cloud-based distributed simulation, remote collaboration, and personalized learning analytics. For military medicine, simulation is critically important for trauma readiness and sustaining skills during peacetime. Military impact is trauma readiness training, battlefield orthopedic injury management, damage control orthopedics, in mass casualty training, and also prolonged field care preparation in large-scale combat operations. We also must provide ethical considerations. As simulation systems become more advanced, ethical concerns increase, including privacy, algorithmic bias, and over-reliance on simulated competency. In conclusion, orthopedic simulators are transforming medical education and readiness. Advances in AI, VR, and modeling technologies continue to improve their effectiveness. These are my references. And provide this quote with Dr. Michael Atkins: "Surgery is the art of healing, and technology is the brush that paints the future." Thank you for listening.